This presentation is about compiling C programs in Linux. These slides were created by Wendy Sanabria and Derek Greenspan, and it is intended for the course CNT6418, which is Digital Forensics 2, this at the University of Central Florida. Now, this course does not require programming. This course does not require programming. As such, though, showing you how some anti-forensics programs are put together and created. So showing you how things work from within a C program that we're going to be writing will help you understand a lot of the anti-forensics, even if you're not a programmer. That's why I spend a week in this class running through programs, and this presentation is just simply going to show you how to get started. The next presentation will actually show you how we're going to create some anti-forensics programs and as an illustration for how they work. So your assignment this week will either be a programming assignment, or I have an alternate assignment for writing a report on a disk image. So there are lots of languages, but what is C? Well, C is a general purpose imperative programming language. And imperative in many ways is kind of the opposite of a functional programming language. Functional programming languages being things like Haskell and Erlang and maybe F#. Other imperative languages might be C# and Java. So those are two that you're probably familiar with. So when you write C programs, they easily map to assembly. And assembly is actually the intermediate step between a source code such as C and actual machine code. Assembly directly maps. C easily maps to assembly, and assembly directly maps to machine code. So this makes it a little bit easier to create compilers for C. So C is considered a high-level language, but of the high-level languages, it's fairly low. It's the lowest of the high-level languages, and that's one of the reasons I really like it, because no, it doesn't do a lot of stuff for you. It's like driving a stick shift rather than driving an automatic transmission. But it's a lot easier to have control over your program. So it appeared in 1972, and it started off assembly, Fortran, CPL, BCPL, and you can't see at the very bottom of the slide, but it should have been B. B was the language that came immediately before C. And C was written specifically for Unix. It was also specifically written in order to solve some of the problems that the B language had. It was written as a response to the inability of its direct predecessor B, the B language, to support byte addressable memory, which limited its usage in operating system design. So C was written to solve a problem. Version 2 Unix was the first version of Unix to support C. In 1972, Unix was rewritten from scratch to C. The modern canonical versions of C are, in order of decreasing compatibility, in 1978's KNRC, and that's still probably one of the most famous ones. In fact, sometimes I write code and I've been told, yeah, it looks like you started off in KNRC. 89 ANSI C, that's really today's standard. If you want to be cross-platform, you're going to write in ANSI C. In fact, one of my students this semester, Derek Greenspan, and I, we commonly, I write programs in Windows C, and then he ports them to Linux C. And as I write them in Windows C, I make sure that they're as close to ANSI C standard as possible, because then if they are, he doesn't have much to do to make sure that it works on Linux. So ANSI C is a really good thing to follow if you're going to be swapping code with other platforms. And there are other versions that came down the pike, but really ANSI C is the one you want to shoot for. So let's talk about GCC, which is the tool we use to compile. It was originally the GNU C compiler. Now it's known as the GNU Compiler Collection, because it's got a number of utilities besides just the compiler and linker that come with it. It's a free and open source compiler plus the utilities that's released under the GNU GPL license. It was inspired by Tannenbaum's, the man who wrote Minix, unfree compiler software. And Richard Stallman, who is a very famous guy, in fact, in class we recently talked about him. He's the guy who wrote the Cuckoo's Egg book, and he was the one who helped catch the East German hackers way back in the day, when even before we even knew, what hackers were and how to stop them and how they worked and all that kind of stuff. But just remember, Linus Torvalds, the guy who originally wrote the Linux kernel, was inspired by Minix to create Linux and used Minix when he created Linux. So GCC was initially compiled on Tannenbaum's compiler system. So it's real easy to compile C files. Compiling a simple program is easy. You just run GCC, the name of the source code, hello.c, and typically a C source code is going to have a C extension. -o is going to be the output, and then whatever the output file name is. Okay, so here I've got an Ubuntu distribution that's running within a virtual machine. Let's go ahead and run a terminal. Alrighty. So I'm going to go ahead and make a directory called hello. It's just off of my home directory. And I'm going to go ahead and create the quintessential start C program, hello world. So we'll say hello.c. I'm going to use Vim as my editor. Okay, stdio, and we're going to talk about include files shortly. But essentially you need stdio just because it's got printf prototyped. And there are lots of versions of main you can use. I'm just using this one right now. And we're just going to do a single command, hello world. Okay, and \n is a new line. So now we're going to go ahead and save this. We'll just do an ls. Okay, it's a pretty small file. Source code is just text. All source code is text. So now we say, I'm going to go ahead and do GCC without any kind of parameters. So it's going to obviously give me an error there. So GCC hello.c, and this is exactly like I showed you from the slide. Now, you don't necessarily have to give it an output file name, but it's a good idea. If you don't, it'll it'll default to something called a.out. So if you forget this, it'll compile and you'll see a.out. But I'm going to go ahead and say hello, and you can see it created that. Okay, so in order to run it, we just do this, and it says hello world, exactly what we told it to say in our program. Now, most of the time when you write C programs, unless they're really trivial like our last hello program was, but most of the time you're going to have more than one source file. Because if you only have one source file, then it becomes huge and unwieldy, and it's difficult to maintain and manage and search through and all that kind of stuff and understand. So what we do is we try to split code up, and we try to group it together in different source code files according to maybe what it does or what it relates to. Different people kind of have their own different approaches. I usually split things up into multiple C files based on sort of their functionality. Then to compile them, all we do is say gcc star.c-o and then the output file name. The star operator, as we've already talked about, is a wildcard, meaning compile everything that ends with .c. Before we even talk about multiple C files, we need to talk about functions. So let's go ahead and do that now. Okay. Okay. Fun functions. make dir fun functions. cd fun functions. So let's go ahead and create a file called getting started. C. Okay. So it's going to be a lot more clear after this discussion why we want to include stdio when we use printf. And I'll come back to that. So we've already seen main. Main is a function, but it's a special kind of function. It's a function that represents the start of the actual program. So the compiler knows that's where you want your program to start. We've already seen this, printf hello world. But if I did everything here within main, the program would get very unwieldy. So what we try to do is we split things up into other functions. And by doing that, we're helping to better organize the program. We're providing what's known as code reusability. So there are quite a few reasons, and this isn't a programming class, so I won't necessarily go into a lot of detail, but I just want to give you the mechanics so we can move forward with our pursuit of anti-forensics programming, which will be the next lesson. So, warm, sunny, printf, love the weather. And if you don't use the \n, these lines will all run together. So you want to, not always, but for something like this, you're going to want to use the \n. Otherwise, everything is kind of windy. Okay, now nothing's actually going to happen. You won't, if you run this program. Let's go ahead and GCC getting started .c. And of course, it defaults to a.out. Okay, so it just says hello world. It actually doesn't do any of that talk about weather stuff. Okay, so you have to actually, so this is a function that has code in it. This is a function that has code in it, but it's not called from anywhere. So we actually have to call it here. We say talk about the weather. Okay. So this is the function up here. This is the actual function. And this is the function call. Okay. Okay. So hello world, and then it does everything that's within that function. Okay. So let's go ahead and continue with this. So let's go ahead and add another function. You can have as many as you want, really. Okay. Talk about my cars. I like my cars. One is a Nissan. First. Oops. One is a Jeep Wrangler. Okay. So obviously nothing here again, the same as with talk about the weather. You'll never see about the cars until you actually make the function call talk about my cars. Okay. So that's pretty straightforward. Now we can actually create functions, say a number, that take parameters. Okay, so there's a whole, and here again, this is just the basics. And the reason I'm going through the basics is so that the next lesson, when we actually talk about the anti-forensic software and programming it and stuff, you'll have at least a general idea. Okay, so the printf statement supports number you gave me is %d is an integer number. And times 5 %d. So just sort of number times 5, just to give you an idea. Okay, so here's the function call, and it accepts a single parameter of a number. And here is where I actually call it and give it a number. Say 7. Oops, I must have done something wrong here. Let's see what I did wrong. Say a number, okay? So make sure you get everything exactly correct, or it won't compile. There we go. Okay. So there are all sorts of parameters you can give functions. This is an integer, one of the most common parameters you'll give a function. You can give it a double or a float. Those are floating point numbers, both of them. You can give it a short. And I might invite you, if you, Wikipedia actually has a pretty good write-up on this, or you can just go somewhere and do a search for C variable types. They're strings, pointers. And for what we're going to do in the next lesson, I'll make sure that I explain everything. But okay, so one of the things you'll notice is that I put everything, all those functions, above main. Okay, and C is what's known as a forward-looking language. And you can actually call a function as long as where you're calling it knows what it is and what it does. Notice here, I just typed in those functions, it called those functions. That's because it knows what those functions are, because they're above main. Okay. Since those functions are above main, by the time it gets to main, the compiler knows what they are. It's different though when they come after main. Okay, so let's go ahead and cut this out. Paste it below main. Okay. So now, by the time it gets to main, it hasn't seen say a number, since say a number comes behind it. So let's go ahead and try to compile that. And we're going to get an error. Okay, so we get an error because we don't have by the time it gets to main, it doesn't know what it is. So there's actually a way to fix that. And the way we fix it is with what's known as a prototype. As long as main knows what say a number is, oops, sorry. This is not the function itself, but this is more like a template for the function. We call them function prototypes. So now it's going to be totally different when I compile. See, no errors at all. Okay, that's because what I did was I told the compiler what I was doing here. It's really just a template. It's not the actual function, and it's not the function body. Notice it's just the function call and what it looks like. Down here is the actual function and its code. But basically, when you put this function here, by the time you get to main, at least main knows what it is. Okay, and so that's why we do that. Oops. Okay, so it compiles with no problems, and it should run with no problems. Okay. Okay, so here's what we had. Just put a little space there. Now, it's not common that we go ahead and we have something like this inside of at the top of our .c files. You can do it temporarily, but it's not a really good idea. So normally what we do is we'll create, let me go ahead and get rid of this. Normally what we'll do is we'll create what's called an include file. And so I'm going to go ahead and create an include file. Let's say func.h. Okay, and .h is the typical extension for an include file. So in my include file, I'm simply going to create the prototype. And save it. Okay, let's do an ls. So now I have func.h getting started.c. So here again, I can't just compile getting started with C. I'm still going to get that same error, as you can see, because I had removed the prototype. So okay, so let me go ahead and add my include file here. func.h. Can save this and compile it. Now it's happy. And the reason it's happy is because rather than have an inline prototype within the .c file, I'm going to put all my prototypes in this .h file, which will give me a better way to organize it. Plus I can use it from other files. Other files can include that same .h. So it's just a much better way to do it. Now instead of having a bunch of messy includes up here, now instead of having a bunch of messy prototypes, I can put them all into one file and access or refer to that file from any other source code file. Okay, so what I'm going to do now is go ahead and get rid of all this. We'll go ahead and get rid of this too. And so now let's go ahead and make a function call. First I'll say hello world, which I've been doing this whole example. But now I'll say a number is 7, and that doesn't exist anywhere. So when I go ahead and save it and compile it, I'll get a huge error. Even though the prototype is in the .h file, the code is nowhere to be found. Okay, so what I'm now going to do is create a separate source code file, and it's going to be called support functions.c. You can call it anything you want. Okay, so say include stdio Okay, void say a number. The number you sent me was, remember %d is the decimal or integer, excuse me, it's the integer number. Decimal would actually be float or double, which would be %f. And times 5, that is %d number times 5. Okay, so now I've got my function there. And this is going to be optional, but this is a good idea. Go ahead and include I normally am going to include it pretty much everywhere. Okay, it's still not going to work though. It's still going to say, hey, I can't find that. But what you want to do is, instead of saying getting started.c, if you just say star.c, say what you're saying is compile all C files into one. We say a.out. Then what it does is it knows to look in that other source code module for that and link it in. Okay, so that's kind of the really super abbreviated version of functions, function prototypes, and multiple source code modules. Okay, so now we're going to do a more complete example, and I'm just going to let you know that just by watching these examples, you're not going to learn a lot. You need to actually go ahead and do this if you don't know programming, which obviously this is not a programming class, but if you can go ahead and sort of follow along with these examples, it will really help your understanding. I'm going to guess that about half of you already know how to do C programming pretty well. The other half of you, just go ahead. You can't hurt anything, so give it a shot. Okay, make dir, let's say temp stuff. Okay, so this will be our more complete example. So let's go ahead and create a main source code file called converters.c. Okay, and I'm going to go ahead and include stdio.h. And the reason that I alluded to before that we include stdio is because it has prototypes for some of the things that we're going to use. Specifically in this program, printf and scanf are two of the functions we're going to use, and stdio has prototypes for those. So that gives you an idea of why we're doing those, what the value of these includes. We're eventually going to have support. We don't have it now, so we'll get an error because we don't have it, but still we're going to go ahead and add it because we know we're going to need it. Oops. Okay, so I'm going to declare some floats this time. Okay. Now we're going to ask the user to type in a number, a temperature in degrees Fahrenheit. And in this case, I'm not going to give it a \n at the end of this printf, because this will this will keep it on the same line, and as the user types in the number, it will be on the same line. Now this scanf function gives the user the ability to type in their temperature. %f means float. Float is a floating number. Remember the last example we used %d, which was an integer. And we have to tell it, we have to put an ampersand in front of input temp. That means it's pointing to the actual input temp variable. Okay. Now the next thing will also give us another error, but we'll be fixing it. Celsius equals convert Fahrenheit to Celsius. We're going to give it that float as a parameter. Okay. Last example, remember we had an integer as a parameter. This will be a float as a parameter. And notice that we're actually getting something back this time. Okay. So we'll say printf, that is %f in degrees Celsius. Okay. Now, if we save this and go ahead and try to compile it, we're going to get several errors. We'll talk about those errors. And the first one is there's no such file as support.h. Okay, so let's go ahead and create that. And support.h is going to have the prototypes for the functions that we use here. So float, convert, Fahrenheit to Celsius. Oops. So it's got an input float, a parameter coming in as a float, which will be the input, and it'll return a float, okay, which will be the converted temperature. Okay, so now if we go ahead and compile that, that error will go away. We'll have another error. The other error is because, oh, it had the prototype and it knew what this happened to be, but it couldn't find it once it tried to link it together. So now let's go ahead and create support.c. These will be our support functions in support.c. So the first thing we want to do is we want to include stdio. Oh no, actually we don't need it because we're not going to do any printfs in here. We'll just include support.h. We don't even really need to do that, but we're going to do it just for because in a lot of cases you will need to do it. So we'll just get in the habit of doing that. Okay. Float, convert Fahrenheit to Celsius, float, input temp. Okay, now this is the actual function body. Now you're going to notice when I save this, it's still not going to do anything. It's still going to get an error here because it can't quite find it. The reason it didn't find it is we didn't tell it that we also want to make sure we got all the other .c files. So if we do this, it compiles. Now, one of the problems is we actually didn't do any calculations, so what we typed in we got back. So now we actually have to go in and do the math. Okay, so let's say float, ret, and we have to return ret. But now we have to do the calculation. So ret equals input temp minus 32.0 times 5.0 divided by 9.0. There are lots of ways you can actually do this. So now let's go ahead and compile it, and it compiles correctly. Let's go ahead and run it. So if we type in 55, we'll actually get a different answer. Why don't we go ahead and type in some well-known, this should give us 100, right? 212. Okay, try it again. If we give it 32, which freezing, in Celsius, that should be 0. So I always test out the well-known numbers just to make sure we've done our calculations correctly. Okay, so that's actually pretty good. We actually have a working program. Now we're going to go ahead and add some more to support.c. And we're going to go ahead and say convert Celsius to Kelvin. So we'll give it a Celsius, and it will return a number for degrees Kelvin. So ret equals input temp minus plus 273.15. Okay. Okay, now we have to add that prototype to support .h. Oops. Okay, there we go. That. And now we're going to add this functionality to our main program. So here, we'll go ahead and declare Kelvin up here. So Kelvin equals convert Celsius to Kelvin. Now instead of the Fahrenheit input temp, we need to give it the Celsius. Okay, say printf that keeps that is %f in degrees Kelvin. Okay, so what we need to do is compile. I did something wrong in support.c. Let's see what it happens to be. Oh yeah, I missed a semicolon here. Now let's try to recompile this thing. Okay, compiles. Say 55 again. Now it gives us both temperatures in Celsius and Kelvin. Okay, very good. That ends the more real, more complete example. Okay, so what I'd like to do is take a little more time and go through two things that you may need to know as we discuss the anti-forensic software in the next lesson. So first we'll talk about loops. And for most of you, this is just going to be a refresher. Okay, so we're going to have I is the most famous counter variable ever invented to man. So I equals, and this is where you're going to start, 1. So you always have a starting value. And then you have a conditional, or sometimes I call it the ending number. So 10. So it's going to count from 1 to 10. And just like in elementary school, you can count by 1s or 2s or 3s. We'll just go ahead and count by 1s. But we'll change all these in just a minute. Okay, so save that. Okay, let me go ahead and make sure I have I here. Okay. Okay. Okay, so it loops through 10 times. So we can actually start it at a different number if we need to. So we'll start it at 3. We'll go to 24, and we'll count by 2s. Okay, just a very small variation on what we had. Okay, so that's called a for loop, obviously, because of the keyword for. We can do the same thing with what's known as a while loop. So if we do it a little differently, while, so the test actually comes first. Let me get rid of this. Okay, so we still have this, we have the condition, we have the start up here, we have the conditional here. Now we are going to have to put the increment here. So we'll make it 4. So slightly different. Anyway, that's kind of the really quick tour of loops. There's actually one more we're going to go ahead and take a loop at. It's a called a do while. So the condition does, you don't start with a condition in a do while. You end with a conditional. Okay, so we have a starting number, we have the increment, and the condition. Okay, so looking at this isn't going to do you a lot of good. If you're already a good programmer, fine. If not, I would definitely suggest that you spend some time with this stuff. Okay, so that's one thing. Now let's talk about some conditionals. So let's say float input number, let's say number 1. Let's say first, second, and we'll have a choice here. Okay. Printf, please enter a number. CNF %f first. We'll just go ahead and do the same thing. Printf, please enter another number. CNF %f second. Now we're going to give the user a choice. Printf operation. Say add. Subtract. Multiply. Divide. I'll say your choice. Okay, scanf %d choice. Okay, so choice should contain 1, 2, 3, or 4. If it doesn't, we'll bail out and tell the user that they needed to make a valid choice. So if choice equals 1, we'll say printf %d plus, let's say plus %d is %d. Okay, so notice what I'm illustrating here is the conditional. If is always followed by some sort of conditional, which is either going to be true or false, and it could be a compound conditional if you want. So we're going to say first, oh, these are floats. Let's go ahead and make them floats. These are all floats. first, second, first, plus second. Okay. If okay, let's just duplicate these lines so we don't have to type all this stuff out, and we'll just edit them. Okay. So now if choice is 2, make it a subtraction operation. If choice is 3, make a multiplication operation. And finally, if it's 4, make it a division operation. Hopefully they won't try to divide by 0. Okay. So that should pretty much cover. Okay, so it's going to save this. And we'll enter a number, 3, 4, and let's go and add. Okay, so it has a bunch of decimal places, but that's okay. We want to link these together. That's one of the things I didn't do, and I didn't do it on purpose. The downside to this, we have 4 separate if statements, and they all are unrelated, so the compiler, or actually the computer, when it runs, it's going to make a choice. It's going to make all these comparisons. However, if we relate them as one family, once it finds the correct choice, it will stop. So this is the preferred way to do it. Also, if we have an else here, this is an unconditional. For if all else fails, we'll say printf, you made an incorrect choice. So that'll give us some sort of error trapping of some sort. Okay. So we'll enter a number, 3, 5. We'll multiply. Okay. Now there's one more thing I want to show you for choices that we could use. Instead of this, we could change it to what we call a switch statement. We'll say case 1. Oops. Case 1. And we actually, back this up a little so it stays on the screen. And then we need a break statement at the end of that. So for each of the potential choices, we need a case statement. And here we need a break. So sometimes this is a lot cleaner to do. It really just depends on, I like to tell students, it depends on, what is most readable for you, as you develop the software. because everybody's brain works slightly differently. So you just want to have code that makes sense to you as you type it. Here we'll have a default. Default is going to be okay if they didn't make any of those choices. Okay. Here I'll go ahead and make an incorrect choice, 7, and it just tells me I made an incorrect choice. So essentially that's the end of the basics for compiling in Linux, and I want to encourage you to go ahead and spend some time, and if you're good at doing this, well, then you don't need any time, but if you're afraid of it, go ahead and give it a shot because the next lesson will mean a lot more.